Hello everyone, in this TRC tutorial number 72 we will explain how an inverter works to generate a sinusoidal voltage with a DC voltage and why it is necessary to reduce the stray inductances. Before discussing the three-phase inverter, I'd like to briefly review the basic three-phase alternator. We have three coils separated by an angle of 120 degrees. The rotor is a magnet and rotates. At t equals 0, the red coil receives the maximum magnetic flux, while the blue and green coils have the same magnetic flux but not the maximum value. During rotation, the blue and green coils will also receive the maximum magnetic flux until the red coil returns to its maximum magnetic flux after a complete full turn magnet rotation. The voltage across the inductor is equal to the derivative of the magnetic flux. We can therefore place a red dot on the voltage plot corresponding to each derivative of the magnetic flux, as shown. We perform the same operation with the other coils to obtain the voltage across each inductor, providing the three sinusoidal voltage sources. Now, if we apply the three sinusoidal voltage sources to a three-phase motor, the rotor magnet will follow the rotating magnetic flux generated by the three-phase voltage and the three coil at 120 degrees angle. The purpose of the three-phase inverter is to create a three-phase sinusoidal voltage with a DC supply voltage. On the left, we have a 300-volt battery whose two red and blue connections are plus 150 and minus 150 volt respectively. On the right, we have a three-phase motor whose three inputs U, V and W are connected to the inverter. The central inverter transforms the DC voltage into three sinusoidal voltages. An ideal inverter should have zero power dissipation because the power at the switches is zero. Indeed, when I is not equal to 0, U equals 0, and when U is not equal to 0, I equals 0. The three-phase inverter is composed of three half-bridges. The next slide will detail how a single half-bridge works. Each half-bridge is connected to the positive and negative supply P and N. Each output of the half-bridge is connected to an inductor connected to ground. Every ideal switch has a diode in parallel to allow the inductive current to flow. When the upper switch is closed, voltage Vp is applied to the coil. At a constant voltage across the coil, the current increases linearly as shown on the load current plot IL. Since the current in the coil cannot be stopped, when the upper switch is open, it continues to flow through the lower diode. Therefore, the coil voltage is Vn, and since the voltage across the inductor is negative, the current slope becomes negative and the current decreases. Each time the upper switch is switched, the current slope rises and falls up to the maximum current and then returns to zero. But the coil current always went in the same direction shown by the large red arrow. When zero current is reached, the lower switch is closed and the coil is connected to the negative voltage Vn. With the negative voltage across the coil, the current slope is negative. When the lower switch is open, the coil current continues to flow through the upper diode, creating a positive voltage across the coil and a positive current slope. By switching the lower switch, the current becomes negative as indicated by the large green arrow. The average current is close to a sinusoid. The positive coil current is shown in red and the negative current in green. We can also graph the average of the voltage across the inductor, which is also close to a sinusoid. Since the coil voltage is the derivative of the magnetic flux and flux equal Li, it is also the derivative of the coil current. By measuring the derivative of the current with the black arrow, we can verify that it is equal to the coil voltage. In this slide, we extract the half-bridge schematic of this IGBT power module with the lower switch QL in blue and the upper switch QH in green. We continue with the parasitic inductances LL and LH connecting the negative and positive power supplies respectively. We also have the output parasitic inductance L out. In the yellow box, we indicate the emitter inductances for QH and QL. The LL and LH inductances are approximately 15 nanohenry, and the internal bonding source inductance is close to 1 nanohenry. We then highlight the source sense inductances SL and SN. The power module with its 15 nanohenry parasitic inductances must be connected to the battery's voltage source. However, this connection is too long and presents too much parasitic inductance. It is therefore necessary to place a high voltage capacitor in parallel with the battery. The capacitor can be replaced by an ideal source voltage and its 7 nanohenry parasitic inductances at each connection. The switching action creates a high DIDT current supplied by the capacitor shown in red. The total parasitic inductances of the power supply are shown in the dotted red box and are equal to 7 plus 15 nanohenry. However, to minimize these additional parasitic inductances, the capacitor should be connected as close as possible as indicated by the red circle and bold red lines. In the image, the blue box represents the capacitor and the green box represents the power supply module. The battery provides a current with a relatively low DIDT as well as the inverter output, which powers the inductor of the three-phase motor. The half-bridge powers the motor's inductance. During commutation, when the voltage drops with a very high negative DVDT, the coil current simply switches from a positive to a negative slope. If we zoom in to observe the falling edge of the voltage, we see that during this edge, the current does not change. Therefore, for the simulation, we can replace the coil with a constant current source. I want to thank you for your attention. In my next DRC car tutorial number 73, we will analyze the switching losses due to the parasitic inductances presented in this video. We will see that even with an ideal switch, we will still lose energy transferring energy from the upper parasitic coil to the lower parasitic coil. So, see you soon and stay tuned.